Hello, this is Dr. Christy Patton-Lukes, a chemical engineering professor at Missouri S&T. In this lesson, we're going to be continuing our study of curve fitting by looking at ways that we can measure and discuss error. So the first of these is the standard error, and I believe you've probably seen this in a statistics course or in other classes where you've discussed statistics. But you have the variance for a data set is the difference between our y estimate, our model, minus the experimental. And if we square those and add up that sum of squared differences and divide by the number of degrees of freedom, that is the variance. Now, the degrees of freedom is the number of observations we make minus the number of parameters estimated. You've probably seen this where what you were trying to estimate was the average, in which case the number of parameters is 1. But in this case, say we were fitting a straight line, then we have m and b, we have 2 parameters, so it would be n minus 2. The standard error is the square root of the variance. But another definition that is frequently used, I see this often in like experimental studies that you see in literature perhaps, is the mean relative error. And this is simply taking the difference between your experimental value and the model predicted value and take the absolute value so that you get positives on each of those and divide by the experimental value. That sum for each of your different data points divided by the number of data points is the mean relative error. But the one that's going to be most important for us is the r-squared value. Now this is set up so that it is always a number between 0 and 1, and the way it's set up is that the closer you are to 1, the better the fit of your model. Now this is going to be particularly useful when we're comparing the different models. Like I want to know, is a quadratic formula better than a cubic formula? Okay. And so I have different number of parameters for these things. So the formulas get kind of a little bit mixed up if I try looking at maybe a variance of 2 different sets. So a better way of comparing different models is to look at the r-squared value. Now, r-squared, in this case they're using y with an overbar to represent the average value. This is the same thing we had done with y in brackets earlier. But if y bar is the average of my observations of my experimental data, then I'm going to have several different sum of squares that I can calculate. One of these is the sum of squared residuals, which is where I take y for my model minus the average y from my data and square that in each case, and that's going to be the sum of the squared residuals. There's also a sum of squared errors, which is simply these deviations we looked at earlier, so the y for the model minus y for the experiment. Those differences squared added up is the SSE value. And then our last one is an SST. And SST is the sum of the square for the treatment. So it's the experimental minus the average and add those up. Okay. Now this R number is 1 minus the SSE over SST, and we usually do it squared because that way, again, we get something that's going to always be positive, so that now then instead of being between -1 and +1, I'm between 0 and 1. And again, my goal is if it's exactly equal to 1, I have a perfect fit. The further away I get from 1, I have an adequate fit perhaps. Depending on what I'm looking at, sometimes, say for the experimental results I got, say in a chem lab back when I was an undergraduate, if I get an r-squared value that's like 0.8 or better, I'm usually kind of happy. But if you're doing something like research quality work, I'm probably looking for an r-squared value that is going to be more like 0.9 or higher. And if it's really high quality research work where you're trying to get a very good fit, you're looking at numbers that are going to be greater than maybe 0.98. If you have large sets of data, say a steam table or something like that, that you know has been repeated by multiple experimentalists year after year, then the R-squared value that you may be looking for may be very high, 0.99 something. Okay, so that's going to be how we use the R-squared. So in our next lesson, what we want to look at is how we can use this as a tool, and we're going to be basing this on tools that Excel has built in. So this completes this little lesson, and I thank you very much for your time.